Before we begin practicing questions, we will look at motion on a horizontal and inclined planes under different cases. It is important to watch lesson 1 to lesson 6 before this lesson, as it brings everything we have done in the previous lessons together. Let's quickly study lesson 7. In this lesson, we'll go through different cases that will be important for solving Newton's laws problems. The first case would be having the motion of an object that is subjected to a force F. So this object is pulled by a force F and is an object that has a mass M along a horizontal frictionless surface. It moves on a surface that doesn't have friction. Now, as you know by now, this would mean that our kinetic friction, because it's moving, is equals to 0. Therefore, our frictional force, kinetic frictional force, is 0 newtons. Now, this object moves with an acceleration a, right? This would mean that this applied force causes the object to accelerate. It means it is the net force as per Newton's second law. So if we want to draw a free body diagram for this object, we know from lesson 1 that we said a free body diagram will change the object and model it as a dot, and we'll draw a force that is applied in that direction. And we already know that gravity will always play a role. There will be the force of gravity going vertically downwards, and there will be a normal force going vertically upwards exerted by the surface on the object. So all these are the forces that the object experiences. Another important aspect here is the reference frame, where we draw our Cartesian plane, our axis, the x and the y axis. In this axis, we choose this side to be positive. It means this side will be negative. And we choose this side to be positive. It means this side will be negative. Now, this will allow us to apply or use Newton's second law if we were to solve this problem. So, remember, Newton's second law, we said that it is a resultant vector, meaning it has the components in the x and in the y. So, if I were to look at scenario 1 and conduct or do calculations on it, I'll look at the x component separately to say the x is equals to the mass times the acceleration in the x. But the net force in the x will be the addition, the vector sum of all forces acting on an object. Remember in lesson 1 we discussed what the net force is. So when we look at this free body diagram here, you will see that in the x direction, I want to use a highlighter. In the x direction here, we only have one force acting, meaning when I add my forces here, I'll have F, and there are no any other forces, then is equals to this guy here, right? Will come down as is. So I'll say M. So this acceleration here, I'll remove the x and write it as A to show that it is this acceleration here, right? And also you will do the same for the forces in the y direction. You look at the y component and you will say is equals to mass times the acceleration in the y. Now, in this case, you will see that in the y, I'll have the normal force, which is this force here going upwards in the positive direction. Then I'll have a plus and minus, right? I'll have a plus and minus Fg, right? Why? Because this force is going in the negative direction. Now the plus and the minus will give me a minus Fg, right, which is equals to m times 0. Now I'm writing my acceleration here as 0. This acceleration here is 0 because the object does not move in the vertical direction. This object here does not go up or down, right? That means the acceleration here in the y is equals to 0 meters per second squared because it doesn't go up or down. It only moves to the right? So there's no acceleration there. That's why it's 0. Now this means I'll have a 0 this side, and I'll have normal force times mass times normal force minus mass times acceleration, because we know that Fg is the force of gravity is given by mass times acceleration. Now this means, let me change my pen. This means that the normal force is exactly the same as the acceleration due to gravity, right? So this is how you'll go about solving a problem where there is no frictional force. The second scenario that you could have would be having the motion of an object on a rough horizontal plane. Now when they say rough horizontal plane, already we know when we discussed the different types of forces, that it means here that we actually now have the coefficient of kinetic friction. It is some ratio here. You'll get a value here, right? It could be 0.05, 0.3, it will be any number from 0 to 1, right? Because we said in lesson 2 that it ranges from 0 to 1 when we discussed the coefficient of friction. Now this means in this case we have the horizontal force that's moving the object, and we have the kinetic frictional force which opposes motion. Again, in this situation, we'll have the object accelerating in that direction with the acceleration a. And the object only moves in the horizontal direction, right? It's going to the right. It does not go up or even down. That means the acceleration in the y is equals to 0 meters per second squared. Now if we draw this as a free body diagram, the object will be modeled as a dot. This is the applied force, this is the kinetic friction force, the normal force going up, and the force of gravity going down. Again, we have a reference frame here that says x is positive when it goes there and y is positive when it goes there. Again, Newton's second law, we said that we apply it in each direction, in each component separately, because the formula net force is equals to mass times acceleration is divided into two. It has the x component and the y component. Now when we look at the x component, it means I'm going to add forces that are in the x direction. Now in this case, I will have the sum of forces in the x is equals to the mass times the acceleration in the x. Now my forces would be F, which is positive, it goes in the positive direction, minus Fk, which goes in the negative direction. Remember that here we have plus and then a minus, then we get a minus. Is equals to mass of the box times the acceleration a, because we're saying it's going to accelerate with this acceleration a. Alright. And if you then go and look at, okay, I can take this effort one step further to say the frictional force would be mu times normal force. So this will be mu k is equals to mass times acceleration. Now, if you look at your y component, the forces in the y, you'll find that it's going to be a times y. Now, in the y here, we would have normal force minus the force of gravity Fg, which is going to be equals to mass times 0, because this object, we said it does not move in the y. Now, this would be m minus mg is equals to 0. So this again means the normal force is equals to mg. Do you see that at this stage we can take this normal force and substitute in this equation here, right? Since in this case, when there's friction, the normal force appears through the formula of friction. So this means here we can say F, the applied force, times coefficient of friction times mass times acceleration, because the normal force is the same as mass times acceleration. And from here, I'm not going to simplify any further, because from here, if you're looking for this force, you can make it the subject of the formula. If you're looking for this, you can make it subject of the formula. If you're looking for the mass, you can do the same. Sometimes they might ask you, but very rarely, to find the acceleration due to gravity, but they never really ask you this because it's a constant. Commonly, they'll ask you the acceleration. It means you can solve that. I mean, if they ask you to solve any of these things, it means you would be having all these other ones, unless the problem, there's other things that you have to do. It's a simultaneous equation, right? We'll do some practice questions on that. So I'm just trying to show you how to break down these questions into small blocks. Another case that's very common and important is the idea of a components of a force. So to understand the components of a force, let's say you have a box, but instead, look at what we're doing now. Instead of pushing the box with the horizontal force, as in the two cases, we actually pulling the box with a force that is diagonal like that. So this force lies between the x and the y. It makes an angle here, theta, right? It makes an angle theta. We say it makes an angle with the horizontal. What does that mean? This means that here it's the horizontal, and the angle above the horizontal here, it is above the horizontal, is called theta, right? So when they say above, you must know that it's an angle that is above the horizontal. If this is the horizontal, the angle is above the horizontal. Now, in this case, what we can do is that we can draw a free body diagram only showing this force and its components, right? I'm not going to show the gravity and the normal force, just for us to understand the whole idea of components of a force. Now, this force will go in this direction on our free body diagram, modeling this object or this box as a dot. Now, what we're saying here, we say this force has the x component and has the y component. What does that mean? When we say something has components, it means it can split into parts that makes the whole, right? So meaning these two, when combined, they make this one, right? So what am I saying here? I'm saying that if you would remember from properties of vectors, that if I have a force going in this direction, or a vector going in this direction, which is fx, and I have another force going in that direction, which is this fy. Remember that I can take this force here, and throw it this side here, right? So that's what I've done. I've basically taken this force and I've moved it this side so that it's sitting like that. This force will remain here. The force F will be here. This is the force F. Now this is 90 degrees and this is the angle theta, because we said here it's theta. We then have a right angle triangle, right? And we know from the properties of vectors that this force then will be the resultant force here, because we have a situation where we're throwing a vector from the tail. So we're throwing a vector from the tail of the first vector to the head of the second vector, right? Remember, that's how we draw our resultant. So f will be equals to fx plus fy as vectors. That's how we'll draw it, right? Now this means that if we were to look for its magnitude, we'll use Pythagoras because it's a right angle triangle. We will say f squared, it's the hypotenuse, is equals to fx squared plus fxy. And if we were to look for the angle theta, we'll then say it is fy over fx. Then you can take the inverse and find the angle theta there. Now these two forces, what we're saying here is that if we were to pull this box, if this box was pulled by a force fx and a force fy simultaneously at the same time, if I were to pull this box in this direction and in that direction at the same time, right, I will have the same effect. The box will move in the same way as pulling it with this force here. That's what we mean when we say these two forces are a component of this force. It means that if I pull this object to this direction and to that direction at the same time, right, it will move in the same way as when I pull it with only one force in that direction. Right, so these two forces have the same effect as this force. Hence, we say this force here is the resultant force, right? Now, already you can see from this triangle also that we can use trigonometric ratios, right, to also solve this problem. If you say here opposite over the hypotenuse, right, that would give you a cos, right? So that will be the cos of theta. So this is scenario 2. Okay, it's scenario 3. That will be the cos of theta is equals to opposite over hypotenuse is the sine, right? So if I'm looking for a cos, actually it will be adjacent. It will be adjacent over the hypotenuse, right? It will be the adjacent side over the hypotenuse, right? Now that will mean I will have here fx, because that's the adjacent side, over f. Now if I solve for that component fx, I'll multiply both sides, remember, here with f and here with f as well. Then the f would cancel. Well, this side it won't cancel, so that I'm only left with f, right? Or you can cross multiply. Yes, you can cross multiply. Here we have a 1, you'll be left with f, and this would also give you f cos theta. That's another way in which you can find the component if you do not use the Pythagoras, right? Then if you say opposite over the hypotenuse, that will be the trig ratio sine, right? We'll have the sine of theta is equals to fy over f. Then when we cross multiply here, this by that, it will give me the f sine of theta is equals to fy. So this means the fy is equals to f sine theta, right? So now that's how you will find the components of this resultant vector here, or resultant force. Now in this scenario 4, what I'm actually doing here is that we using the idea of a component of a force, and we now include other forces, your friction, normal force and the force of gravity, because now we know how to resolve this force, right? To resolve means to break it into its component, into its pieces that makes the whole, right? So now in this case we applying the force in that direction, right? It makes an angle theta above the horizontal, right? But there is now friction and there is normal force included in this gravity. So when we draw the free body diagram, you can see that all those forces are there. But very important, I also included these forces in orange to say the force F has the x component and the y component, as we explained in the previous case just now, right? So now this is very important, because when you apply Newton's second law, you then have to include those components in the x and in the y. So when we look at the sum of forces in the x, it will be equals to mass times acceleration in the x. Remember that our object will move as a result of these forces. It will move with an acceleration a, right? Now this means when I'm looking for my net force, I would say F in the x because it's positive minus Fk because it goes in the negative direction, right? Those are the only two forces acting in the horizontal, is equals to mass times the acceleration, because we're saying it's moving with an acceleration a. I can expand this as we did in the previous one to say this is the normal force is equals to ma. But now if I look at the forces in the y direction, I'll then have mass times acceleration in the y, right? And then I'll have normal force plus the y component, right? Minus Fg, right? And this will be equals to m times 0, because it does not move in the vertical direction, this object, right? At this stage you would see that there's a lot of things that I can change here. The normal force plus this component, we said when the scenario is like this, it will actually be f sine theta, right? It will be f sine theta. So here we'll have f sine theta minus mg is equals to 0, right? So this means here that the normal force is equals to mg is going to be positive when it goes to the other side, minus f sine of theta. Do you see now that in this scenario the normal force is not equal to the force of gravity? It's actually the force of gravity minus the y component, right? We're subtracting the y component from it. Now this can be substituted in this formula, right? So when we come here, we can end up having fx, remember we said it is f cos theta. So here we can have f cos of theta minus mu k times mg minus f sine theta is equals to ma. Now I'll leave it at that, because from here this is like, there's many pathways that we can take. We could be asked to calculate the acceleration, we could be asked to calculate the mass, maybe we could be asked to calculate f, right? We could be asked to calculate the coefficient of friction, right? Using that formula. So I'll leave it at here because it will depend. I'm just giving you ways of how to manipulate these equations when you deal with them. I guess this makes sense and you are following, because I know these equations they tend to be complicated, especially when you start having components and a lot of things going on them. we'll move to an inclined plane. Right, we'll move to an inclined plane. We'll look at case 5. Right. Maybe before I move to this, I also want to explain something about components of a force. To say that how does one spot a component of a force? The best way to spot the component of a force would be that if you have a force that is between the x-axis and the y-axis, it's in between this force, then it must have the x component and the y component. It will give you this type of a diagram there, the right angle triangle, right? Which explains the fact that it is the same as pulling this object with these two separate forces individually. You'll get the same effect as pulling it with one force, like there. This is different from pulling the object with a force like this. Already this force is a component, it is in the x. It's different to pulling it like that, because when you pull like this, it means I have components in these two directions, right? So when you have a force that is in the vertical or in the horizontal, already it is in component form. But if you have a force that is between the x and the y, it must have components. This came in mind when I was looking this diagram of an incline, because that's how you'll really see the components of an incline as well. So an incline means that we have a surface that is not horizontal, a surface that is arranged so that it is like this, and there is the horizontal here, meaning we have an angle theta here, right? So the angle here will be theta. Let me use a pen to write this one. The angle here will be theta. Now, if we have a box that is on this surface, as usual, the force of gravity, we know and defined it in lesson 4. I think it was lesson 4, that it always points vertically downwards. The earth always pulls any object towards its center, right? So this will be our FG. Now, in this case, you will see that the x-axis should always be parallel to the surface, right? So we'll draw our reference frame so that the x-axis is parallel to this, and obviously if this is the x, the y have to be like this. It has to make a cross like that. That's how we draw our Cartesian plane, right? Then with that type of arrangement, you will notice that the force of gravity is actually between the x and the y-axis. And because it is between those two axes, it must have the x component, the component in the x, and the y component, the component in the y. Now, these components are sometimes given names to say the x component is sometimes called the parallel component of gravity, right? So this means that it is the component that is parallel to the surface. So this component here is parallel to the surface, right? And the other component, the y component, is called the perpendicular component of gravity, right? So this is a component, it is perpendicular to the surface. It makes a 90-degree angle with the surface, hence it's called the perpendicular component. Or you can simply say it's the x and the y component, because it lies on the x-axis and it lies on the y-axis, hence we call them that way. Now, if you look at this diagram that we have now, the situation that we have now, I can take this force here, right, and actually draw an equal vector this side of that force. So this force here would be Fg in the x, right? So that now I have a right angle triangle. Here it's 90 degrees, right? there is one thing that you need to memorize. Don't worry about proving it at this stage. Is that the angle here is the same as the angle of the inclined. The angle here is the same as the angle here, right? So if here is 30 degrees, also here it will always be 30 degrees. If here it's 15 degrees, even here it will be 15 degrees between your forces. So sometimes they'll give you a problem and they'll give the angle of the inclined. Automatically you must always know it will be the same angle as this one here. Now what we have done now here is that we have a right angle triangle, right, and we have the angle theta. That means we are able to now find these two components, right? If I were to look at the x component, you will notice here that the angle is sitting here. This will be opposite over the hypotenuse, right? So what I'm saying is that this will be the sine of theta. Sine of theta will be equals to the opposite side, which is fgx over the hypotenuse side, which is this side here, right? And that would be this side here. It's fg is this one, fg. So this will give me the fg. Then if I cross multiply, you would see that our x component will be equals to fg sine theta, right? The same can be done with the y component. Now if you look at the y component, if we say here that adjacent, the side adjacent the angle, right, over the hypotenuse, that is a cos, it's a cos of theta. It's a cos of theta is equals to fgy over the f, because it's our hypotenuse. Then when you cross multiply, you should be able to get fgy is equals to fg cos of theta. Now with cross multiplying, remember I'm cross multiplying this and this, it gives me that, and here we remember we have a 1, invisible 1, we'll get that. You can go a further step on these equations really, because we know that fg is the same as mg, so we can write that as mg sin theta. We can also write this as mg cos theta. Now these formulas here, they will always be like this. They will always be like this, regardless of whether the inclined it's like this or the inclined it's like that. These forces will always be defined by this, and the x component will always be mg sin theta, and the y component will always be mg cos theta. I'm saying this to you because when you are dealing with this type of a situation where you have these components here, let me refer to this one. When you have these components here, right, as in this diagram here, these formulas can change. They are not always like this. They depend on where this force is pointing. If it's pointing to this direction, they will be like that. But if the angle were to be changed, maybe it's here, the angle is here, they will also change. Or if we put our force like that and we put the angle here, they will change. They will not always be given by your x component will not always be given by f cos theta. It might be f sin theta, right? And also this can change to a cos theta depending on where the angle is and how is your force, in which quadrant is your force placed. That will play a role. But in terms of an inclined plane, it will always give you these formulas, right? It will always give you these formulas. Another scenario that's worth looking at. So here basically I'm doing the same situation as we did here at the top, except now here I'm going to include the normal force and the frictional force, because remember, if we were to put a box on on an inclined plane, right, the force of gravity will act such that it has these two components, and what will happen is that this component here will start pushing the box to go down, and that means the surfaces here will be in contact with each other, producing the frictional force, the kinetic frictional force. And if this force is not large enough, the frictional force here will be static, the box won't move, right? But if it's large enough, it will move, so that there is kinetic frictional force. Now, and of course, the box is in contact with the surface is pushing the box with a normal force N there, right? So now again, if you were to apply Newton's second law in this scenario, you will see that if I look at the x components, if I look at the x components, it will be mass times acceleration, right? And in this case, my x components would be mg, the sine of theta, right? Because it's this force here, right? It's going in the positive direction, because we said x is positive according to our reference frame there. And remember, I just said now that the x component will always be mg sine theta. It will always be mg sine theta. The x component will always be mg sine theta, right? So that is our fg, and I'm subtracting on that, right, the kinetic frictional force, which is mu k times normal force, is equals to mass times acceleration, right? So I'm subtracting this force here because it's going in the negative direction. Now, if we were to look at the y component, you will see that we'll have the normal force, which goes in the positive direction. It goes up like that, and then we subtracting from the normal force mg cos of theta, right? And this is equals to this is equals to 0, because this object here on the inclined, it does not move in this direction. There is no acceleration in this direction, right? The acceleration is 0 meters per second squared. It's only moving, it's sliding down like that with the acceleration a here, right? So this would mean now that the normal force is equals to the perpendicular component of gravity, the component in the y direction, right? And as usual, we can take this and substitute it here, right? So that we then have mg sine theta minus mu k mg cos of theta is equals to mass times the acceleration. Again, I'll leave it at this point, because when we are here, we can be asked in an exam to calculate any of those variables. You can be asked to calculate the acceleration, you can be asked to calculate the coefficient of friction, or even the mass of the object, right? It depends on how the question can be structured. Now, those are the basic cases that you may come across in an exam, and you should be comfortable with manipulating those equations to get the desired results, right? I just put those so that we can prepare to solve our questions, right? And they put everything that you have learned in one place. Following these lessons would be the last two lessons where we'll be doing questions. We'll start with multiple choice questions followed by long questions. See you in the next two lessons. May the force be with you.